Welcome to the Higher Structure Seminar, and this week our speaker is Julia Plavnik from Indiana University and now currently visiting University at Hamburg, and she will talk on the classification of modular categories. So we welcome her and thank her, and yeah, please.
Thank you, Ilham, so much for the introduction and for the invitation. I'm very happy to be here. And yes, the idea of this talk is to give a panorama about the classification of modular categories. My plan is to introduce what a fusion category is and a braided category, and then tell you about some interesting invariants, the classification, and then some more specific results. But if at any point you have any questions, please feel free to interrupt me, or if you want more details, let me know, or more examples or something. So maybe just a small comment that I wanted to say, a little bit the motivation why to study, why to classify modular tensor categories. And here this asterisk here is to remind myself that there is a disclaimer. Here when I say modular tensor categories, it's just kind of by historic reasons. It should be maybe more appropriate if I say modular fusion categories, because I will be always in the fusion case in this talk. But we have use always this term of modular tensor categories, and I will abbreviate it MTC. So why? There are many reasons, in my opinion, to study these modular tensor categories. One is because they appear everywhere. They appear in connection to many, many areas of math and also many areas of physics. So, for example, low-dimensional topology, where you studied topological quantum field theories, was actually the way that these modular categories started being studied, jointly with the physics viewpoint of that. Also, like in connection with knots invariants or links and knot invariants. Also, mathematical physics and the study of CFT, conformal field theories, and vertex operator algebras. A lot of the times you will hear that these MTCs are the shadow of the vertex operator algebras or the conformal field theory. So there is a deep connection between these things. The way that I started studying, maybe, and I should say this, because I'm an algebraist, so this was the way that I started studying this, by studying quantum groups and Hopf algebras, because the representation theory of these algebraic objects give rise to nice tensor categories, and many times they are modular. Also in analysis, when you study von Neumann algebras or planar algebras or subfactors, there are relations to this topic. And in particular in physics, what I was saying, different physicists are interested in this. For example, people studied condensed matter because modular tensor categories are a model for certain topological phases of matter, for two-dimensional bosonic topological phases of matter. So they are useful for topological quantum computing, for example. But also high energy physicists are interested in this area. So it's very nice. I like it because I can learn about different topics all the time. And the other thing is that in some sense, you can think about these modular categories, or maybe more generally about tensor categories, I should say, about tensor categories as natural hosts for quantum symmetries. So in the classical world, when we study symmetries, we think of groups. But now when we study quantum objects, the symmetries of these objects are not longer described sometimes by groups. Sometimes groups are not enough. And tensor categories are the correct language, are more like a unifying language between different things, and in particular for quantum symmetries. So maybe before going to the details of the talk, let me say why classification, because some people find classification boring. Things like, okay, yeah, we will classify for the sake of classifying, for the sake of finding some results, because it's interesting for ourselves and only ourselves. But actually, classification has given rise to many interesting things. For example, this theory of tensor categories, and in particular modular categories, is kind of a young theory. So we don't have as many examples as we would like to have, or as we would need. So one way to finding new examples is via the classification. For example, these n-Ising categories, which is a family of categories that has certain dimension, a power of 2, they were found via classification. People was classifying and they found these new families of things and they started studying these new examples. Or also when you're classifying, sometimes you get inspiration and you see some patterns appearing, and that's what happened for us. We were classifying categories and we were able to come up with a new construction of modular categories, or actually fusion categories. We were classifying fusion categories by dimension. We were looking at dimension 36, and we found an exotic fusion ring, and that was related to one that we knew coming from quantum groups, but was not the same. And in this way, we did this new construction called SESTing, but was inspired by classification. And also sometimes when you want to understand invariants and properties, they come more clear when you're looking at classification questions. So for example, people were studying classification by rank of modular categories. And if you don't know this word rank from per dimension or all this, I will say it in a minute or in a couple of minutes. But when they were studying this classification by rank, they came up with a Cauchy theorem inspired by the group one, but the group theory one, this one in the setting of fusion categories. And because they were inspired by classification. So classification not only give us a list, and also for physicists, it's important, classification, because they really want a periodic table of these topological phases of matter, and classification gives you kind of that idea. But also for all these other theoretical reasons, I think it's very interesting. So what I want to do next is give you the definition of a braided fusion category. And I want to do it by an example. And after looking at this example, we can write the explicit definition. If this is too boring because you already know this, let me know and I can go faster. But what I will do is I will use this example of representations of a finite dimensional representations of a finite group to give you the idea of what a fusion category first and then a braided fusion category is. Maybe one disclaimer here, you saw that I wrote the complex. In general, you can do this for a field, but maybe keep in mind that for what I'm saying, I need the field to be algebraically closed, and in particular, I will work to characteristic 0. This is less drastic to drop sometimes. You can drop it and you change some things and you get well-behaved most of the things, but dropping algebraically close gives rise to a lot of different results. And my former student's thesis, Sean Sanford's thesis, was about studying when this doesn't happen. But let's talk about this case, about the complex, if you want, in your mind. So given what we like about this category, about these finite dimensional representations of the group, and this group is also finite. One of the things that I think are useful is that if you give me two objects here, when I consider the maps between them that are the intertwiners, this is itself a vector space, which in a category in general, this will be a set of morphisms, the maps that respect the action of the group. In this case, they form actually a vector space, so it's nice. Also, if you give me two representations, I can give you a new representation that will be the tensor product. As a vector space, is just the tensor product of vector spaces, but then I need to tell you how the group act, right? And in this case, it will be just the diagonal action. The other nice thing, here, let me change it so I have the field, is that the field is an object in our category itself. How? Via the trivial action. So I will not do much here, just the trivial action of the group. So I have the trivial representation. And the other nice thing is that if you have a representation, you can consider the dual vector space, but moreover, you can endow it with an action of the group. How? If you give me a linear functional, I can act on it. And the idea is that I will get another element here. So I need to tell you what's the value in B. And what I will do is I will do T. I would like to know T at V, but actually I will act here because remember that my V is a representation, but I will not act by G. I will act by the inverse of G. And this is the contragradient representation. For people that maybe it's familiar with Hopf algebras, this can be easily generalized to Hopf algebras here. And here, what gives rise to this diagonal action is the co-multiplication, to the trivial action is the co-unit, and to the contragradient representation is the antipode. So representations of a Hopf algebra are another nice example to keep in mind. Then, because of Maschke theorem, we know that every representation of our group is completely reducible. So what I mean with this is that every representation of my group decomposes a finite direct sum of irreducible representations. In this case, that's why I'm using characteristic 0 here. If not, you need to say something about that. Or in the worst case, it will not happen that, and it will not be semi-simple, but that's fine. The other nice thing that we have is that we could consider the flip, right? These are vector spaces, so we could just flip the two elements. But what is nice here is that this is a map in the category. So what I'm meaning with that is that it's an intertwining, so that respect the action. So if I act here and I flip, I get the same as first flipping and then applying the action. And this is because here I'm doing just the diagonal action, okay? So that's nice. I have a commutativity for my tensor product. So now maybe let me tell you what's a fusion category over a field. And what I'm doing is just kind of repeating the same things that we said before for Rep G, but now in a more abstract way. So the first condition that I will ask, or the first structure that I will ask, is that my category is abelian. So I want to have a direct sum, kernel of morphisms, co-kernels, a zero object. Maybe I should say that first. Basically, what I want to do is I want to be able to have exact sequences in my category. And the other thing that I will ask is that my category is C-linear, K-linear, which this was the first condition that I wrote. The home spaces in my category will not only be sets, they will be vector spaces. Vector spaces over the field. And this is the K-linearity. So the spaces of morphisms in my categories are vector spaces, so that's nice. The other thing that I will ask is adding more structure. For now, I have a direct sum, but also now I want to have a tensor product, which was the second thing that we said in the other case. So what I will ask is for having this tensor product that I want it to be associative. So I will ask for having an associativity constraint. Now for categories, we don't ask for equality, we ask for maps. That are isomorphisms. What this map is doing is saying that putting the parentheses in the left when I have three objects is the same or is isomorphic to put it in the right. Then the other thing that I will ask is for a distinguished object in my category, which will play the role of a unit for this tensor product. So I want this tensor product to be unital. And to say that it's unital, I need to have two other maps, left and right unitors, basically saying that X tensor 1 is isomorphic to X and one tensor X is also isomorphic to X. And this is not all of it. I also need to have some nice diagrams, which we call the pentagon and triangle axioms. These ones just said that the ways to put the parentheses are coherent. So if we have four objects, there are 5 ways to put parentheses on it. That will be the vertices. Here, if you compose the maps that you could imagine to complete this diagram using associativity and identities, both the diagram is commutative. And the same here, and in this one I will have the left unitor, the right unitor, and the associativity. So this is monoidal category. So now I will ask for a property. I have my monoidal category and I will ask for a property. I want that every object in my category has a dual. But the dual is not just another object. So for every X in C, I want this to have duals. Actually, I want this to have left and right duals. And why I say it's not just an object, because I also want to have a map that is called the evaluation, and a map called the co-evaluation, and as usual, I will have some axioms. These are called the zigzag axioms, which basically what it's saying is what it's written in the drawing, that when you have these kind of diagrams, you can actually strike the lines. And this diagram here, if you're not familiar with graphical calculus, is fine. These kind of things will be talking about, if I'm reading like this, the diagram, it's kind of, I'm creating something. I start in the vacuum, I'm starting the unit, and I'm creating a particle and an antiparticle. That's what I'm doing here. So it's this co-evaluation map. And this one like this is the evaluation. So it's the annihilation of things. I have a particle and antiparticle, and I send it to the vacuum. This one is more usual, what you would imagine with an evaluation map. So I want to have duals for everything. The next thing that I will ask is the one that came from the Maschke theorem. I ask for semi-simplicity. So every object can be written as a direct sum of simples. And this is what it was meaning before irreducible representation. So simple means that this is simple in the sense of abelian categories. I don't have an object is simple if the only sub-objects are itself and the zero object. So this is a condition or a property of this. This is a property here. This one is also a property for this one. Now I will ask for finiteness. Finiteness, since I already asked for semi-simple, is much cheaper. The only thing that it asks is that there are only finitely many simples up to isomorphism. Again, I always care only up to isomorphism. The definition of finite is longer, but since I already asked for semi-simple, many things come for free. So the only one that I want you to keep in mind is I will have finitely many simples. And this is very nice because now I kind of have a basis for my Grothendieck ring. So doing fusion categories in some sense is like doing higher dimensional linear algebra. It's a way to think about it, not exactly, but a way. And the last thing that I want to ask here for this first part is that the distinguished object here, the monoidal unit, is a simple object. So this condition here is the one that mixes these two things together, because being simple is related to the abelian structure, being the unit is related to the monoidal structure. Okay, so this is the definition of a fusion category. If you drop semi-simple, what you have is a finite tensor category, which are also very interesting, but we will focus on the semi-simple case. And now the last thing that we had before, the flip, is related to having a commutative tensor product. And in category theory, we call it braided. So this fusion category is braided if there is a family of natural isomorphisms that make my tensor product commutative, plus two hexagon axioms. What are these hexagons? These hexagons are telling you that the braid behaves well with the associativity, or maybe before, with the tensor product and with the associativity. So this hexagon, what it's doing, it's comparing how, for example, this compares with this and this. And there is a formula that you can do. And basically, when you do this, you get something like the braid equation when you do it in the strict case, meaning that this and this are all identities. And there are two axioms, because imagine that you could put the tensor product in this side or you could put it in this side. I was not going to write the braid equation or the strict case, but if you want, I can do it. But I don't know if you have questions before I keep going. Okay.
I have a question.
Yes,
What if the number of objects is infinite? Does it break something?
Things will not work in the same way. For example, when I study a modular category, one of the things that I do is or one of the invariants that we have are some matrices. And many of the things work well because the things are finite. Or for example, we define a notion of a dimension for C, and that is the sum of the square of the simple objects. So that we will not be able to have it. But there are people that study infinite, let's say, tensor categories. For example, people that study C-star algebras or maybe something with von Neumann algebra, a lot of the cases they have are not finite. I'm not sure what other techniques they use, but you can study that things. It's just that the way that you study probably will be kind of differently than the one that we use to approach the problems. I don't know if that makes sense or if that answers what you were asking.
Yeah, thank you.
Thank you for the question. So let me give you one example that also comes from a finite group, but this time is with vector spaces. So the categories that I will be looking at are finite dimensional, G-graded K vector spaces. So the objects are just vector spaces that admit a grading by the group G, and these are subspaces. And I mean, and the vector space is finite dimensional, okay? What are the morphisms in this category? In this category, the morphisms will be, imagine that I always have here this structure first. I have vector spaces, so I want, first of all, to have, or to respect that. So these maps here, will be linear transformations to start with. But now I want this to behave well with the grading. So I will ask that preserves the grading. And now I need to show you that it's a tensor category. I want to find a tensor product. So the tensor product as a vector space will be the tensor product of vector spaces. But now I need to tell you what's the grading. And what we will do is we will have a convolution-like product. So we will do this. We will tensor all the possible components in V and in W that when you multiply together the labels, give you G. And then we add that. And that's so this is kind of a convolution. Tensor product. Sorry, my tensor didn't look nice. Okay. So this is the formula. And I need to tell you who is the unit. And we know from the cases of vector spaces that the unit or the vector space that makes the tensor product unital is the field, right? If you tensor by the field, you don't change nothing. So this need to be K as a vector space. But I need to tell you the grading. But this only has subspaces 0 or itself. So it's, maybe let me say, this is this concentrated in degree E, where E is the neutral element or the identity element for my group. All the other components will be 0. So it will be K in degree E, and in all the others is 0 because I don't have anything else to put there. And you could tell me, okay, yes, that's fine. But what if I do the same for other degrees? Because I could look at the other objects that are one-dimensional, basically, but are concentrated in other degrees. And that's a fair question. Actually, that ones are very important objects in this category. I will call them delta G, because they are the field concentrating in degree G. So basically, this is the object in my category that when I look at the grading is 0 if the grading level that I'm looking is not G, and it's the field if it's G. And in particular, with this notation, delta E is the unit from before. These are all simple objects because you don't have any sub-object because the vector space doesn't have any subspaces. And actually, these are all the representatives. So these are all the simple sub to isomorphisms. The other nice thing is that when you look at this piece here now, at the tensor product, I mean, if you look at this tensor product, seems complicated. But when you look at this simple object and you look at the tensor product, this cannot be that complicated because as a vector space is still one-dimensional. The only thing that you're changing is in which degree is concentrated. And it will be just mimicking, sorry, this doesn't look like an H, but mimicking the multiplication of the group. And the dual will be the inverse. Let me say one more thing. Now, if you give me any of these vector spaces, you can write it like this. And something that happens in regular vector spaces is that any vector space can be written as certain copies of the field, right? We're infinite dimensional. And in this case will be something similar, but degree by degree. So we will have here dimension G copies of delta G. So as you see, this category is semi-simple. How you get it? In each degree, you put as many copies of this simple object as you need. So this is a nice example. Let me now talk about the associativity, because I have never talked about the associativity. So what will be the associativity? In this case, will be some map that change parentheses from left to right. I can do it in the simples because everything else extends by linearity. But if you look who is this, basically remember that these are just, the tensor product is just doing the product of the labels, right? And now I don't really need to put the parentheses because in a group, the parentheses don't matter because the group multiplication, it is associative, right? So if you look, you get a map from this simple to itself. Now, for abelian categories, we have Chur's lemma that tells us, maybe I will not write it, that when you are in a abelian categories and you look at a map between two simples, the map is 0 if the simples are not isomorphic, or the map must be a multiple of the identity if the map are isomorphic. If the objects are isomorphic. So in this case, it's not only that the objects are isomorphic, but also this is an invertible map. So this will be some multiple of the identity of this object. And I will call this multiple omega GHF because this multiple depends on GF and H. And this will be just an element in the units of the field. And now there is a nice fact that you remember that we need to satisfy the pentagon axiom. Having the pentagon axiom is the same as showing that this omega is a 3 cocycle. So the pentagon axiom reduces as to the 3 cocycle condition. Now, I'm not going to go in details unless there are questions about the braiding and about the modularity in this case. But the braiding, just if you're curious, is related to a quadratic form of the group. And for the category to be modular, this quadratic form needs to be non-degenerate. Maybe I can say just this. So there is something called, maybe let me say this, there is something called, for braiding, at the end I'm saying it, there is something called abelian cohomology. And this abelian cohomology can be extracted or maybe not extracted, the opposite, kind of encode in a quadratic form. And then MTC if and only if this quadratic form is non-degenerate. So I wanted to, before going to some results on classification, I wanted to mention some notations and invariants, but I don't know if you have questions before that. Okay, if not, we can continue. So the first thing that I wanted to mention is when we were talking about the definition, I mentioned this finiteness that then Victor asked about. So in this case, we will be in the finite case. And what we were looking is at the number of, or we were looking at the number of elements of simple objects. So the first thing that we will do is we will look at the set of the simple objects and always up to isomorphisms. This we will denote just because the relation with group, we will denote it irreducible of C or ir-C. And since this is finite, we will write something like this. And the first object will be the 1 because we asked that one to be simple. And there is an important invariant that it's a number, that it's the rank, that it's one of the things that I mentioned before. The rank is just the number of simples. So here it doesn't look like an R, but this is R minus 1. It's a number of simple objects in my category, or isomorphism classes of objects in my category. And this has been very important. People have been studying classification by rank a lot. So I tell you how many objects I have, and we try to classify using that information. Other very, very important thing that we look at are the fusion rules. I told you, if I have 2 objects, in this case, I'm looking at simples, but in general, if I have 2 objects, I could tensor them, and I get a new object. But now my category is semi-simple, so I can decompose them as a direct sum, again, of simples, and up to certain multiplicity. Each of them will appear with certain multiplicity. Here, it's also important to use finiteness to write this sum here, and semi-simplicity also. If it were infinite, you could do something again, but maybe you need to be more careful. But simplicity is very important. Because of semi-simplicity and finiteness, we can do this higher dimensional linear algebra approach that I was saying. Because now, if you see, everything can be encoded in matrices, basically, all the information. And these are multiplicities, so these numbers are actually non-negative integers, right? So this will be very important and are called the fusion rules. Moreover, these numbers are encoded in the following way. Remember that we have this Grothendieck ring, and the simples, or this set, is the basis for that ring. So I could look at the operator of multiply by one of the simples in the left, and I want to write the matrix of that with respect to this basis in the Grothendieck ring. And the matrix basically is given by these fusion coefficients. That's what we are doing. So this matrix is very important, and it's very nice because this matrix only has non-negative integers. So using the Frobenius-Perron theorem, one can, or remembering that theorem, we know that this matrix has a maximal non-negative eigenvalue, and that will be what we denote by, or what we call the Frobenius-Perron dimension of xi. And this is always happens to be a positive or a non-negative real number. Actually, for these simples, for the simples, this is always positive. And this is important because it doesn't need to be an integer. This dimension could be a square root of 2, could be the golden radio. There are examples of this. It's not also totally out of control, but could be more interesting thing than just integers. And I will make some comments later about this. One other way to think about this Frobenius-Perron dimension is that it behaves very nicely. It's closed, or respect maybe is the word, but no. So it respects direct sum, tensor product, it's unital, and it's invariant under duality. Okay, so the Frobenius-Perron dimension of the sum is the sum of the dimensions. The same with the product. The dimension of the unit is 1, and the dimension of x and x dual is the same. So basically, this is giving me a character of the Grothendieck ring, and a very special one. And then using that dimension, we can define the Frobenius-Perron dimension of the category itself. And this comes a lot from representations of groups. And it's related to this idea of the character degrees of the irreducible representations that give you back the order of the group. So the formula is that one, coming from here. The square of the Frobenius-Perron dimension of the simples give you the Frobenius-Perron dimension of this. These are definitions. So maybe let me tell you a little bit more about this nice invariant that I like a lot. It's a strong invariant. For example, there are some nice things that you could ask to your objects. One, for example, is to be invertible. What's the definition of being invertible? Remember that we have these nice maps, evaluation and co-evaluation map. The object is invertible if these maps are isomorphisms, which makes kind of sense with what we are asking, because we are saying that X has an inverse for the tensor product. It's just that it's not any inverse, it's that it's the dual always. So what we're saying here is that X tensor X dual is isomorphic to 1 and X dual tensor X 2. And we will denote by GC the set of all the invertible objects in my category up to isomorphisms. This is nice because this is a group under the tensor product. The unit is the unit of the category, and the inverse is given by the duals. So this is a nice group to keep in mind, attached to your fusion category. Why I say that the Frobenius-Perron dimension is in a strong invariant? Maybe checking that something is an isomorphism, I don't know, maybe it's okay, but maybe sometimes it's hard, or maybe you don't even know that directly who this is. But this can be detected, invertibility can be detected by the Frobenius-Perron dimension. An object is invertible if and only if the Frobenius-Perron dimension is 1. So that's nice. And actually there is a nice definition that a category is called pointed, a fusion category is called pointed if all the irreducible all the simple objects are actually invertibles. So all the simples have dimension 1. And then we could do this less strong. Instead of asking that all simple objects have dimension 1, we could have asked that all the simple objects have integral dimension. In that case, we call the category integral. Or even more, we could soften even more the request and ask that the dimension of the category is integral. If you see, this implies this and this implies this, but all the implications in the other directions don't work. Let me tell you what we know about these kind of special categories, because you see I'm requesting a lot here. I'm just staying kind of the safer cases. So let me tell you what we do know about them. These ones, the pointed ones, the one that all the simple objects have dimension 1, are very well understood. They are always of the form of one that we know, the vec G omega. And I forgot, actually. Let me go back here, because I did this, but here I should add this omega here, which is this omega here. The notation encode the omega without, sorry that I didn't wrote it, yes. So when you have this pointed case, you understand quite well how the category looks. It's related to vector spaces, a finite group, and a tricocycle. Now, for integral, we also have a nice result by Tingovnik, Schick, and Ostrich. This is a more classical result of Heidelberg, Mike Lane, probably. But for integral, we also understand, not like we really, but at least we know how they look. They are always representations of H, where H is a finite dimensional, semi-simple, quasi-Hopf algebra. I mean, I say more or less we understand, because not like we have a classification of finite dimensional semi-simple Hopf algebras, much less quasi-Hopf, but at least we know more or less how they look. They are representations of H. And we know that sometimes some of these don't coincide with this. That's why we know that this doesn't happen. Not all rep H are coming from this or have this shape. For example, rep G for a finite group that it's not abelian will not be of this form, basically. But now these ones are less understood. And part of or at the end of my talk, I want to attack this problem, or at least tell you some ideas of this. But what it is known, maybe let me pick another color. What we do know is that in this case, the dimensions of the simples are a square root of an integer. So they are more crazy, they are not an integer, but not super crazy. They are square roots of an integer. So that's what we know. But we would like to have a better characterization like what we have here or here, right? Okay, so maybe now let me go to the status of the classification of small modular categories. The first thing that I know that this is a lot of information, so don't stress, I will go part by part. I just wanted to write here what we know. So the first part is this classification by rank that I was telling you, this number of simple objects. Victor Ostrich started this in the more general setting, not modular category, but fusion categories. And he gave a classification of rank 2 fusion categories. But imagine rank 2 is not a lot, it's this unit and one extra object. In this case, there are some interesting categories. For example, the Fibonacci categories is here, and then representations of groups, and not much more. So this was well understood in generality. But when you want to go to rank 3, it's already hard, and you need to add an extra hypothesis, pivotal. Pivotal is related to the ability of having traces in your category. And to be fair, I cheated a little bit because I told you the definition of braided. I never went to the definition of modular. And if we have time at the end, I can tell you it's a little technical. That's why I skip it. But one of the things that you ask is these traces to exist in a modular category. We ask for something called spherical. So it's related to this idea. But you see, already to have 3 simple objects, and one of them is the unit, I have to ask for more hypotheses. So it's hard. There are some partial results for rank 4, but it's not complete. So many people have worked in the classification of modular. Until here, I didn't ask for modular, but now when I go to modular, so Paul Bruglia, Agustina Chenki, Richard, myself, Eric Rowell, Stone, and Wang were kind of the pioneers in the modular case of using the modular data to do this, and many other people have worked on this, a lot of people. And I should have said here, because he has done a lot of good work on this, and he's a physicist actually, so maybe let me add here. Xiao Gauguin has a lot of interesting things, and now they push classification up to rank 6. Still, imagine it's not wow that far, but I know I have been in communication with some of the people like Eric and Xiaogan, and they say they probably will be able to push it soon to maybe up to 11. Or maybe a little bit more. So it's not like a lot what we know for general modular categories. So I will start asking for more hypotheses. So the first one that I will add to the list is, what if I ask my modular category to be weakly integral? Remember that weakly integral was that the dimension of the category is an integer. In this case, remember that the dimension of the simplest word is square root of integers. Okay, with some of my collaborators, we could push in that general case up to rank 7, which now doesn't look that far, but at the moment was only a classification up to rank 4, I think. So we push it a little bit more adding this. But when, moreover, not only you ask for integral, but also you ask for odd, with Agustina Chenki, we push it up to 15. That's a little bit more. And I will make comments about this because we think we can go much further in this case in a little bit. So this will be the focus. The odd dimensional will be the end of the talk. Then this year, and this is a very, very like new result, I would say, or this year result, Zhengwei Liu, Sebastian Palcu, and others pushed the integral case. Integral is when the dimensions of the simples are integers. They were able to push it up to rank 11. So it's a nice progress. And that probably will help this general case. No, sorry. This general case a lot will help also to push it. So that's by rank, that's the number of simple objects. The other thing that we have done a lot is studying the dimension of your category. Like when you study, for example, the order of a group, classification by the order of the group, that's kind of the idea here, but we use the, as I mentioned, the analogous will be the Frobenius-Perron dimension of C. So Ettingov, Chelaki, Nikchik, Ostrich, and others have worked on this, including myself, also Paul Brouillard, Sonia Natale, Dong, Rowell, me, and others. Here, these are the cases that people were studying. Dimension P a prime. Here, P and Q are always prime. P, PQ, PQR, P to the N, P to the A, Q to the B. This is just not a classification, but it's a Burnside theorem. So some of the times we are not able to classify, but we are able to characterize. In this case, they prove that these categories are solvable. That's what they prove. And with some other people, we work on these cases P to the N times M, with M is a square-free integer. And there is also nice advance in this, but there is still work to do, and it gets harder and harder. There is another invariant that I didn't talk about, which is called the quantum dimension, that also people have studied some classification, but there is not much progress on that yet. The other, and this is more or less new, this is from 2020. These two are much older, but this is from 2020. The modular categories have a Galois action by certain group. And people have started studying how they can classify or how much they can say about the structure of the modular category or their classification if you fix the number of orbits. So Richard Ng, Elon Wang, and Qing Zhang, they starting this study, and they starting by studying transitive modular categories. So when you have only one orbit under this Galois action, and they give a very nice paper and very nice classification. But already going to two orbits, which is what we did with Andrew Chupre, Qiqiang Yu, and Qing Zhang, and myself, it's already hard. We didn't even were able to complete it. There is one case missing, but we did a lot of progress, and we show also that going up in orbits will be much harder. Even the other extreme case, which will be that the numbers of orbits, the number of simples, will be very, very hard. That's much harder. The other thing here was the Frobenius-Perron dimension of C, maybe let me say here. But the other thing that people were studying was the dimension of an object that generates your category. This comes a lot from subfactor theory. So there is work of Afzali, Scott Morrison, Dave Pennis, Kennedy, Michel, Izumi, and others. And there is there are classifications up to this dimension of the generating object. This generating idea is because they use subfactors and planar algebras, but people also have studied, in particular me and my advisor when I was doing my PhD, classification, and maybe here I should say more like characterization, in this sense of solvability, group theoretical, or these kind of things. And what is the CD of C? Is the character degrees of C. So this is an analogy with groups, and basically we try to impose restrictions on the possible dimensions of the simple objects of C, and then we classify given that. For example, if you ask that all the simple objects have dimension a power of certain specific prime, or things like this. And the other, and again, there are more. For example, here, as I mentioned, there is also quantum dimensions and so on, but I wanted to give a sample, at least a sampler. The other thing that people did, and again, is more related to this approach of subfactor idea, they look at the tensor generator of the category. Not all the categories have this tensor generator. That's why these are for special categories, but the subfactor categories usually have this one. That's why I say that this is this approach. And Scott Morrison, Emily Peters, and Noah Snyder they have a beautiful paper, and they studied something called trivalent vertices. So they bound the multiplicities, and this was kind of the formula that they gave, and in this case they have a nice classification. So for categories with this generator with these fusion rules, they give a nice classification. So maybe let me tell you some conjectures that there are open in our area that I feel like this is a very, very important conjecture. I call the weakly integral conjecture. Not like I call, but it's a weakly integral conjecture. Remember that this means that the dimension of C is an integer, this weakly integral condition. I told you, if it's pointed, we know that it's back G omega, so come from G and extrico cycle. If it's integral, it comes from a quasi-Hopf algebra, representations of a semi-simple quasi-Hopf algebra. But if it's weakly integral, we don't know how they look. So this conjecture addressed that topic. And what Ettinghoff, Nikschik, and Ostrek proposed a couple of years ago is that if C is a weakly integral fusion category, it always can be constructed from groups in certain way, and they call it weakly group theoretical. So here I don't want to go in this moment to the technical definition, but let's say that can be constructed from groups and cohomology. Not as explicitly as we said with the back G omega, but basically, maybe let me say a little bit, in fusion categories, we also have a notion of Morita equivalence, and there will be a notion of nilpotency, and saying weakly group theoretical is saying that it's Morita equivalent to something nilpotent. So, and that one can be described from groups. So what we're saying here, or the conjecture is that if it's weakly integral, can be described in terms of groups and cohomology. But this is open, we don't know. So checking that something is weakly integral is easy because computing the Frobenius-Perron dimension is easy. But then if you know that your category is weakly group theoretical, weakly integral, in principle, you don't have that much to work with. On the other hand, checking that something is weakly group theoretical is harder, but working with something weakly group theoretical is easier because it's all group and cohomology information. That's why this would be very nice to have because it will connect these two things. One disclaimer is that weakly group theoretical implies integral. So the opposite direction is true. We want to know if this direction is true. We don't know this direction. So maybe when I was doing my PhD, Natalia and myself, we proved that when C is a fusion category that has dimension odd and C is weakly group theoretical. So here I'm asking for weakly group theoretical. Let me stress this. In this case, we can prove that C is solvable. Again, I didn't define solvable. It's Morita equivalent to some nice category, which is called cyclic nilpotent. Why I call it Fay-Thompson for weakly group theoretical? Just because I'm asking, remember Fay-Thompson for groups is the order of the group is odd, then the group is solvable. Here is the same idea. So if you have a fusion category with odd dimension and the fusion category is weakly group theoretical, we can prove that it's solvable. The usual question is that if we reprove Fay-Thompson, and I wish that, but no, we use it because again, weakly group theoretical means that I can construct it from groups. So we use it, that in that case, the group needs to have odd dimension, or odd order, sorry, and then it's solvable, and we use that. The more general conjecture will be this one, that it's if I have a fusion category with odd dimension, and now I'm dropping this condition, the conjecture is that in this case is solvable. This conjecture goes in hands with this other conjecture. So this implies this one too. So it's not like a crazy conjecture, but this will be very nice. And actually this is enough to prove it for modular. It will imply also the fusion case. So this would be something that I would love to know. And to end the talk, I wanted to present some results that these are joint work and I think I mentioned her before with Agustina Chenki. She's a student of Victor Ostrich now. She's also from Argentina, and this result came actually from her master thesis or undergraduate final project. So we were working together, and then we wrote this paper later. So let me tell you a little bit about odd dimensional, which was one of the cases. So if I have a fusion category and I know that the dimension of the fusion category is odd, I mean, what I know there is that it's weakly integral. But actually, in that case, it must be integral. And this kind of follows from a result of Jelaki and Nikchik. So in principle, we would expect the dimensions to be square root of integers, but in this case, we know that they are integer. So this is kind of Hopf algebraic flavor of problem, or quasi-Hopf algebraic problem. And moreover, if you have, maybe I should delete this, I don't need a fusion category. Of odd dimensional, then maybe I will say here an MTC to be on the MTC. I want to have a modular category with odd dimension. Then in this case, having odd rank, remember that the rank is the number of simples, is equivalent to my category being maximal non-self-dual. And I didn't explain this, so let me tell you what it is. Self-dual means that X is isomorphic to the dual. It's its own dual. Being maximal non-self-dual is that this can happen only in one case, which is the case that always this is true, which is when X is the unit. So this is the definition. That if, I mean, X simple here, maybe here. So if I have a simple that it's self-dual, must be the unit. So for odd rank, this is always true. In the modular case, when the dimension is, maybe here I can say an integer, but yeah, an odd integer is also true. Sorry, when it's an odd integer. So what was known before we started with Agustina to think about this, Paul Bruyère and Eric Rowell proved in 2012 that if the rank of the category is at most 11, then the category is pointed. So here I'm saying CMTC odd dimension, an odd rank. Yeah. So pointed maybe odd rank. Which, if you remember, this means that it's Beck G omega. The other thing that they show is that for 25, C doesn't need to be pointed. I mean, it could be pointed, but they are not all pointed. And why? Because you have representations of the double of a group, and this group is set 3 semi-direct sub 7, the non-abelian group. With this group, you can construct a Hopf algebra called the double, and this one gives you a rank 25 category that it's not pointed because this group is not abelian. So the natural question, the follow-up question is, okay, what happens if I have something in between, right? For up to 11, it's fine, it's pointed. In 25, doesn't need to be pointed, but what in the middle? The current conjecture is that all these are pointed. That's the current conjecture. So in 2020 with Agustina, we proved that up to 15, we can always show that this is pointed. But if the rank is between these other two, then C is pointed, or the group of invertibles is just one. So what I'm saying is that they have only one invertible. And why this would be interesting? I think of Nikchik and Ostrich proved that if C is solvable and C is not Beck, then this group of invertibles cannot be one. So what this is telling me here is that if one of these categories here exists with this, so if there is C with rank, I don't know, between 17 and 23, and this is 1, then this category cannot be solvable because it's not Beck, the rank of Beck is 1, and doesn't satisfy this, so it's not solvable. No, maybe, no, sorry, maybe not solvable, then. But this will be a counterexample to the Tinkovnik-Ostrich conjecture, because this will imply that this is not weakly group theoretical in this case. And that will be a counterexample. So counterexample to both to the ENO and the Fay-Thompson conjecture. But more importantly to the weakly integral, maybe let me say here, conjecture. So this is what we are very interested. We think that this is always pointed, to be honest. We think that this can be discarded, and we have a student thinking on this. But in general, we think that it's interesting to attack these all-dimensional categories with that dimension. And sorry if I went over time, and thank you. And if you have questions or comments, please let me know.
Thank you very much for this very interesting and wonderful talk. So let's thank our speaker. So any questions or comments? So maybe I will ask one very naive question, but it is like a meta conjecture kind of thing. My impression is that many group theoretical concepts are translated into the language of fusion categories, or they appear. And my impression is that the grant project is how we classify finite simple groups or such thing. Maybe we want to make a classification like that of such categories. Is that so?
I think there are a couple of things. Most of the examples that we know at the moment come from groups, Hopf algebras, or quantum groups more in general. So I think, for example, one interest of this, maybe let me go here, of this conjecture. So personally, for me, it would be nicer if the conjecture is false, because that will give interesting examples. That will be my preference. But if not, okay, it's nice, because also will let us understand more the boundary in which these categories change from being like groups than were don't. So that's why I think this conjecture is interesting.
Right.
It's very interesting. And in general, we are trying to understand more the panorama, because honestly, most of the examples that we have come from maybe these more understood structures, like I was saying, groups, Hopf algebras, quantum groups, subfactors. The most exotic examples are subfactors. And the other thing that people try to do a lot of the time is, okay, I found this new modular category or this new fusion category. Is this related to one of the ones that I know via some construction? There is Morita equivalence, Witt equivalence, and other constructions and things. So these are the kind of questions that we are thinking now, but I think it's also because we still don't have that many really new things, and that's what we want to know, what is really different, what is really new, how much we can get from fusion, or how much we can get from groups in the fusion category setting. What are the difference? I don't know if that answer, or maybe I started saying
that perfectly answers my question. So, for example, there is this notion of solvability and non-solvability, and that reminds me of, or when I hear something solvable, immediately Galois theory comes to my mind, for example. Is there some sort of Galois theoretic category version or connection of these theories?
The Galois theory that we have in mind is more for modular. The solvability could also be defined more in general. What there is kind of going on there is this Morita equivalence relation. One of the things that it's slightly strange is that there is a notion, maybe let me add a page here. So for example, there is a notion of nilpotency there's this notion of solvable.
Right.
But this is not true,
Oh, I
for
see.
example, which is weird. But if C braided, then yes, then nilpotent implies solvable.
I see.
So for fusion, no. And it's another thing is that it is defined at the Grothendieck ring level, or maybe in terms of fusion rules. It's not defined in terms of fusion rules, but you can decide if the category is nilpotent only looking at the fusion rules. In principle, this is not.
I see.
But we don't know, maybe, but we would like to know if depends or not on associativity, for example. So in principle, this definition is more involved. It's not because it's defined in terms of this Morita equivalence. This one is just defined in terms of fusion rules. So looking at the fusion rules is enough. For this one, in principle, no, but I don't have any, and this is a question that people think, I don't have any example in which the fusion rules are not enough. Because, for example, what I was trying to prove here, this, or not like this conjecture, this Frobenius Perron dimension here only depends on fusion rules. So in this case, maybe it only depends on fusion rules if this is true. So we don't really know, but yeah, I mean, the Galois theory that I have in mind is usually more for these modular categories, not that much for this, but might be interesting to see if there is something else going on there.
Yeah, thank you very much. So any questions or comments? Okay, then I will stop recording now.
Okay.